Okay, so we are talking about push down automata. Just to recap, so it's a tuple like this: Q, sigma, gamma, delta, Q0, Z0, and F. So Q is the set of states, and this is the sigma is the set of input alphabet, and this is the symbol in the stack. So here we have a stack, as you know, and delta is the transition rules, which is taking the input as a so the delta is a function from Q. We are at some state and we take a input alphabet in the tape along with the epsilon, and then we read a top of the stack. So we have given a, so suppose this is the input symbol in the tape, and this is our finite state machine, and we are at some state Q, and it is tape is heading here, and this is the stack, and which is initialized by Z0, and the initial state is Q0, and this is the initialized by Z0. This is the situation initially, and initially nothing is there in the input. The suppose A is the input. So, this is the initial situation, but after that we have some stack symbol like Z is the top of the stack, and we have our state is at some time Q. Q is the state, and this is the situation. So, this is a function of Q, a state, and a input alphabet A, and a stack symbol Z. So, stack symbol is coming from here, and Z0 is the initial position. So, this will consist of, this is non-deterministic. So, this will consist of some of the sets like Pi gamma P1 gamma 1 like this, Pk gamma k. Now, suppose we have option here, non-deterministic move. Suppose P comma gamma is belongs to this, and our PDA, this is push down automata PDA, or PDA is going to this state. So, that means this will be, so after this the new state will be, so tape head will move to the, so new state will be P, and tape head will move here, and this will be Z will be replaced by gamma. So, say this is gamma. So, gamma consists of some Z1, Z2, ZL say. So, this is ZL minus 1 dot 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 say Z1. So, this is our gamma, and then after that it will point to the again the top of the stack. So, this is the situation, this is the movement by the PDA. So, it will move to the, it will replace the Z, the top of the stack symbol, by a string of stack symbol. So, that string is the gamma. It could be epsilon also. So, this gamma could be epsilon also. So, in that case that stack symbol is erase kind of thing, and it will move to the next part of this, and using this we have defined what is the ID, instantaneous description of a automata. So, that is the snapshot of the present state of the automata, like we have the initially our initial state is, yeah. So, we will define that. So, this is we have already discussed, but just to recap, what is the ID again. So, suppose initially we want to read a, this is the our tape, we want to read A1, A2, A3, AN. Suppose there are n input, and we start with the our journey from the state Q0, and the stack is like this. So, stack initial stack symbol is Z0. Now, it is pointing to the this and the this. So, this is the our just if you take a picture snapshot of the automata, this is the situation. So, what is the situation? We are at q 0 and what is the tape? Tape is nothing but this one W A 1 A 2 A n, which we are going to read. And what is the stack condition? Stack is only one symbol, which is Z 0. This is the situation. Okay. So, this is called instantaneous description. This is the initial ID, if this is our W. Now, suppose after this, if we read delta, so this is delta of depending on the, so q 0 A 1 Z 0. So, depending on that it will have a move. So, suppose this is going to some of the state, suppose it is going to say q 1 and this will replace to this belongs to this, and we have there could be many other options, but we have decided to go q 1 and this Z 0 will replace by gamma. So, what will be the next situation? Next situation is like this. So, our tape we have already read A 1. So, now our tape condition is like this A 2 A 3 A n, and where we are at q 1. Q 1 is the next state. I mean we are choosing that, we have option. And what is the stack situation? So, stack is gamma. So, gamma say consists of some say Z 1 Z 2 say Z L, okay, or say Z k. So, gamma will be replaced by Z 1 gamma Z 0 Z k. So, this whole thing is our gamma, and this is the top of the stack. So, it will point to here and this will point to here. So, if you take the picture of this, now the situation is now our stack condition, the automata condition is we are at q 1 and our this is our tape and our and our this thing is gamma. This is the current snapshot of the automata, and we can say this ID, from this ID we are moving to this ID. So, this is the move relation from one ID to another ID. So, this we have already defined. So, using this move relation we can define the language accepted by the automata, and then today we will show their equivalency and we will define the deterministic push down automata. So, just to define formally the move relation, suppose this is our ID q A w and say some Z alpha. So, that means that this is the current situation. That means what? That means this is our tape, we have a and we have W over here, the string, and A. So, A is a alphabet input alphabet and W is a string of input alphabet. W could be empty also, and Z is a string. So, we have Z is not a string, Z is a symbol top of the stack, and this is our alpha stack symbol, and we are at our automata at q 0. So, this is the current ID, current snapshot of the PDA. Okay. Now, suppose this P of, so we are now we need to take this delta move on this A. So, delta of q A z. So, it may have many options, this is a non-deterministic. Now, suppose this belongs to, it is having say this option P, it is q is going to P and this Z is replaced by gamma. So, gamma is again a string of alphabet. So, here Z is a stack symbol, gamma is a string of stack symbol and alpha is a string of stack symbol. Okay. So, this is the situation. Now, suppose it is going to, so this is going to a new state P and this we have already read A. So, now situation will be W and then this z will be replaced by gamma. So, now this will be the new snapshot. So, this is our w and this will be pointing here, and we are at p now, and our stack is like this. So, this up to this is alpha and this is replaced by gamma, and this is the top of the stack and this is the situation. Now, what is the current in description, current snapshot of this? So, our state is p and our tape is we have to yet to read w, and the stack condition is the z was replaced by gamma. So, gamma is again a string of stack symbol. So, gamma and alpha. So, we can say this is the move relation. So, this ID to this ID we are moving by the transition rules of the PDA. Okay. So, using this move, so we will keep on moving this. So, again from this ID, if we move to some other ID, like we take this delta of P, then say suppose this is A1 and then suppose this is Z1. This may go to some other thing. So, that will be coming into the picture. So, that will be the move relation. So, if it is going to say some R and then say Z1 is going to replace by gamma 1, okay, then we say this is going to R and so suppose A2 A3. So, A2 A3 AN is the situation and the gamma is this still there. So, gamma is consist of say Z1 Z2 Zk. So, it will be like Z1 is replaced by again gamma 1. So, gamma 1 Z2 up to Zk is there and alpha is still remain there. Okay. And we say from here to here we are moving in two step. So, we can say from here to here we move in more than one step. So, like this. So, this is the move relation recursively, reflexive transitive closure. Okay. So, using this move relation we have defined the language accepted by this PDA. So, there are two types of acceptance of a language. So, this just a recap, this we have already defined in the last week lectures. Language accepted by a PDA. So, we have given a PDA say Q sigma Q0 Z0 F is the final state. Okay. Now, our initial ID is we are at Q0 and we say W is the string we need to read. So, we put the W in the tape and the initial stack symbol we are using Z0. Now, suppose this is going to repeated applying of this delta rules. If we can reach to a situation like this, some QF and we must end up with reading this string, this is epsilon and we have some gamma in the stack. Stack should not be empty. Once the stack is empty, you have to hold there. There is no further movement if the stack is empty, because this delta is a function of Q, then C input symbol including the epsilon and the stack symbol. So, once this is empty, then we do not have any move, because here we have no epsilon is there. So, then we have to hold there, stop. Okay, that is a stopping condition or halting condition. Okay, so, situation is like this. So, this is the, if QF is the final state, then this kind of string is called language accepted by. So, this is set of all W sigma star such that this where QF is a final state. then we say this is called language accepted by final state. Okay. Language accepted by final state. So, that means we start with this situation, we are taking A1, A2, this is our say W, okay, and initially we are at Q0 and our initial tape condition is like this, a stack condition is like this, and we are keep on applying these rules and we are changing the IDs. So, the snapshot, and slowly if we move to this situation, we exhaust reading the string, there is nothing left in the ID in the this, and if we reach to some of the final state and we do not bother about the stack, because this is the language accepted by the final state. So, now we define the language accepted by the empty stack, then the so we must emptify the stack. So, that is defined as n of m. This is the set of all string of input such that start with Q 0 with this W and Z 0, it must go to, we do not care about the state, because this is not in terms of the language accepted by the final state, it is in terms of the language accepted by the empty stack. So, this is epsilon and this is also epsilon for any state. For any state, we do not care about this, Q. So, that means stack should be empty. I mean, along with the once we finish the reading the this what is called input tape, input in the tape, then the stack should be empty, we should able to. So, then this is called language, this is the language accepted by the PDA accepted by empty stack, and this will be we will use this in a more often, because this will be will show that the PDA is eventually accepting the context free language CFL. There is a equivalency, for a given context free language we have a PDA which is accepting that language, accepting in the terms of empty stack. But we also discuss the equivalency between these two. That means, if given a PDA which is accepted by the final state, then we have a language which is we can have a PDA which will be accepted by the empty stack. So, this equivalency we will discuss. Okay, so, this is just a recap. Now, today we will define deterministic PDA before we move to the equivalency is of these two. So, deterministic push down automata. So, a automata, a PDA which is again this tuple delta Q 0 Z 0 F is deterministic if, I mean, for non-deterministic the delta was a so what was delta for in the PDA? So, delta is a function from q cross sigma, we can take epsilon also, and this gamma, and this is going to the power set 2 to the power q along with gamma star. So, that means, if you take a earlier one, if you take a q, and A. So, suppose this is the situation, you have A and Q is the current state, and say top of the stack is Z. So, we are reading Z. So, Q Z. So, for non-deterministic, here we have many options, like we have P 1, gamma 1, P 2, gamma 2, P n, gamma n. Okay. But here for deterministic, we do not have this, we have a deterministic move. Either this will be empty, either this delta of Q A Z is either empty or it is a singleton set. Singleton set, like this will be only one move. We do not have non-deterministic, it is a deterministic move. Either we do not have any move or we have a deterministic move. That means, this will be like this, say P, and this Z could be replaced by gamma, only singleton set, or it is empty. Then this is called then this is called deterministic PDA. That means, this move is deterministic. Okay. It has only one element in this this thing. So, now what we will show? So, we can have some example of a deterministic PDA. Let me check if I have one. For deterministic PDA, yeah, I think I have one. Let me take this example. Suppose we have a M like this, Q 0 and say Q 1, Q f. These are the states, and we have A B C. These are the sigma. This is our Q, and we have a stack symbol. Stack symbol we are using A B Z 0. And we have corresponding delta, we have to define delta, and then Q 0 is there, Z 0, and F is Q f basically. F is Q f. So, this is Z 0 and we have Q f over here. So, this is the states, and if we define the delta like this, delta of say Q 0 A Z 0, this is the singleton set Q 0 A Z 0, and delta of Q 0 A is equal to, we can write this in a graphical form. So, this is Q 0 and we have Q 1 and then Q f. So, we define delta of Q 0 A. So, if we are Q 0 A along with, if we have a move, if the stack symbol is say Z 0, sorry, stack symbol here is Z 0. So, this we want to write. So, stack symbol is Z 0, input is A and we are at Q 0. So, this will be replaced by, so we are remain at Q 0 and the stack symbol will be A Z 0. So, this is the way we do that, and delta of Q 0 A. So, if we have A and if the stack is also A, then this is going to replace by Q 0 A. So, this will be Q 0 A. like this. Okay. So, only one move is there. So, yeah. So, let us write this here. Now, delta of A. So, now delta of Q 0 A B. So, Q 0 A B, suppose it is again at Q 0. So, this is also singleton set Q 0 A B. So, if we Q 0, if we have a input A and if the stack is B, then the stack will be replaced by Q 0 Q 0 A B. A is the stack. So, Q 0 A B. So, this will be replaced by Q 0 will be remain same, the stack will be A B like this. And then if we have from Q 0 to delta of Q 0 B Z 0, this is we are going to have Q 0 B Z 0. So, this also we can write here. If we have B, if we have B and if stack is Z 0, then the stack is going to replace by B Z 0. This is about and we have one more, and delta of Q 0 B A. This is going to replace by Q 0 B A. So, if we have a B and if the stack is A, then it will be B A and will be remain at Q 0. Okay. And Q 0 B B, Q 0 B B. So, this will be remain at Q 0 and this is B B. So, Q 0 will be remain. So, B B. So, B and B. So, will be B B. This is all rules of Q 0. Okay. So, now with Q 1 with C we are going to Q 1. So, let me write the rules for C. So, let me erase this. These are the rules from Q 0 with A B. Now, let me write the rules for Q 0 with C. So, Q 0 C small c A. This is going to Q 1 A. So, that means, if you have input C and the stack is A, then stack will be remain at A. Okay. And again similarly, delta of Q 0 C B, this is also same as Q 1 B. So, the meaning is, so if we have a C and if the stack is B, it will be remain at B. And similarly, Q delta of Q 0 C Z 0, this will be again Q 1 Z 0. So, this is C, if it is Z 0, we are going to Q 1 and it will be remain at Z 0. Okay. So, this is the rules with Q 1 and C. Now, we have a rule from Q from Q 0. Now, we have a rule from Q 1. So, from Q 1 delta of Q 1, if we see A and A is the input. So, this will be say delta of which is basically Q 1 epsilon. Okay. So, that means, if we have a Q 1 and if we see A will be remain at Q 1. So, we have a over here. So, if we see A and the stack is A, then this A will be erase, and Q1 if we see a B and if the stack symbol is B, we are going to erase that. If we see a B and if the stack symbol is B, we are going to erase this. Okay. And from Q1 if we see a C or epsilon, this is the final step. From Q1 if we see a Z0, we can go to QF epsilon. So, that is the final step. So, from here with epsilon, and if we see a Z0 in the stack, so this will be empty. Okay. So, this is the rule, and this is the final state. This is the final state. So, this is one example of deterministic PDA. So, which language it is accepting? It is accepting by the final state, it is accepting WWR, all the palindromes. W is belongs to AB star. This one can easily verify. Okay. Thank you.